Okay, 6 p.m. Glasses are so damn dirty. Okay. Okay. Okay, welcome back. So, we're just going to pick up where we left off. Now, I want you to know that the topics that we're about to cover are going to be hard to think about for some people. Not that it's like hard to think about in terms of having emotional responses or anything like that, but hard to think about in terms of it's gonna bend your brain a little bit, and it'll be even worse in the next lecture. But don't worry about it. I'm not going to ask you to know any math. I'm not going to ask you to know anything like that. What I want you to do is listen to the story, and I want you to look for some specific things here. I want you to look for type 1 thinking errors. They're going to play a major role in the story I'm about to tell you. And specifically, they play a role in driving discovery forward, right? Scientists are going to think they see one thing, but it turns out to be another. What I also want you to pay attention to are the anomalies. If you remember, an anomaly is an observation that seems to violate the laws of nature as they're currently understood. It's a paranormal event by definition. And the role that these anomalies play is that's the catalyst for driving the science forward and making progress. So I want you to pay attention to those two aspects of what we're about to talk about. And also, that my phone going off just prompted me. I just want you to know that I am on call starting today. So I'm going to be on call until Wednesday next week. And so that means if I get a phone call, I'm going to have to answer it. I just spit all over my computer. But anyway, if I get a phone call, I'm going to have to answer it. I'm not trying to be rude or anything, but I'm on call. So probably won't get a phone call, but if I do, that's what I'm doing. So just to recap, we started with Ptolemy, who was the first guy to really was credited with putting a coherent cosmology together called astrology. And the properties of astrology were that it was geocentric, so the Earth is at the center of everything. It was geostationary, which means the Earth didn't move. And he explained epicycles using perfect circles with imperfect circles. And we got to the Copernican revolution, which took place about 1,500 years later, in 1580. And what prompted that was the invention of the telescope. And there were some observations that were made by Galileo through the telescope that contradicted the Ptolemaic worldview, or the astrological worldview. And those observations were that Jupiter had moons around it, which of course challenged the notion that everything was revolving around the Earth. The sun had sunspots, which challenged the notion that the heavenly bodies are perfect. And then he noticed that the planet Venus had phases, kind of like the moon has phases. You know, sometimes the moon is full, sometimes you have a half moon, sometimes you have a quarter moon, that kind of thing. Venus had those same characteristics over the course of a year. Sometimes you would see a half disk, sometimes you would see a quarter disk, and none of the other planets behave this way. So Mercury and Venus, they behave this way, but Mars, Jupiter, and Saturn did not. And the only way to explain this was to put the sun at the center of the solar system. And you had Mercury, Venus, and then Earth. And so that means that we would see those inner planets from behind sometimes, which accounts for why they have phases. But we never see the other planets from behind, which is why we always see them sunny side up. So that's an example of an anomaly that could not be explained by the previous paradigm. So there had to be a paradigm shift to the heliocentric model. And so that's where we are now. Okay, so let me start the presentation here. We're with the model with the Copernican model, here are the key features. The zodiac is still used as a celestial coordinate system. That's going to be kept throughout this whole process. We're now heliocentric, so the sun is at the center of everything. The Earth moves. Planets orbit the sun in perfect circles, so they kept the perfect circle concept. And of course, they got rid of they explained retrograde motion just by simply putting the sun at the center of everything, so they didn't have to have epicycles. Okay, so with that in mind, here's your first question. And by the way, when you answer these questions, answer them through Top Hat. Don't answer them through Zoom or anything like that. I was throwing some people off last time. So here's a question. What is the underlying cosmology or underlying assumption of Copernican cosmology? Is it that the sun is at the center of the universe or the Earth? Should be an easy one because we just talked about it. And if you're having trouble answering for some reason, just remember, email me after class and I'll take care of it for you. Oh, you're welcome. Yeah, that's a pretty neat feature, huh? Okay. All right, good. The sun is at the center of the universe. That's exactly right. So to remember this, just remember Ptolemy with a P. It's spelled with a P. It's pronounced Ptolemy. It's spelled with a P. That is Earth-centered or geocentric. Copernicus is sun-centered. Okay? Now we're going to move on to the next one, the next paradigm shift. And remember that we talked about there were certain properties of science that make it unique. And those properties are that it changes the way we think about nature. The goal is to predict and control nature. And there's an error correction mechanism built into it by design, right? And it produces knowledge. Another unique feature of science that exists nowhere else in any other human activity is a very special kind of paradigm shift called a synthesis. And a synthesis occurs when two independent lines of scientific research come together to make something new. They basically, each line of research has these questions that remain unanswered. And this line of research over here answers the questions of the other one. And so they interlock with each other. And they answer each other's questions that were unanswered previously. You can see synthesis all throughout science in modern day. Hold on, I'm going to put the code in the chat. So some examples. Biochemistry, right? You have the merging of biology and chemistry into one coherent science. Electromagnetism. Previously, two independent lines of research, the study of electricity and the study of magnetism. It turns out that they were two sides of the same coin. They were different aspects of the same phenomena. So now we have the science of electromagnetism. Right? There's plenty of examples of this. It is a unique characteristic of science that this happens. What we're going to talk about here is the synthesis of classical physics, the very first example of this happening in history. And during the Copernican revolution, a man named Johannes Kepler developed the laws of planetary motion. And these laws described how planets move about the sun, and they were very accurate. In fact, it was the first time that scientists had used equations, mathematical equations, to describe natural events like this. So it was all the rage. It was brand new. They were very precise. The mathematics was very appealing to people because it was so precise, and you could use these equations. You'd input some numbers, and out comes your result. Now, what Newton did When he saw the comet appear in 1680, he thought, maybe I can apply Kepler's laws of motion to explain the motion of the comet. Now, he had to do some interesting tricks with the math to make it work, because the comet was a very different kind of orbit, and basically he imagined that there was this force of gravity, but he had to find a way to tease it out of the data. So in order to do all of this, in order to make these calculations possible, he had to invent a new math and a new form of mathematics, and that mathematics is called calculus. So what he did, when he discovered gravity through this process, it was like finding the missing piece of the puzzle. You had Kepler's laws of motion, which described how planets move the way they do, but they didn't explain why. What Newton did is he came along and he provided that missing piece of the puzzle. He explained why. And it's like, why do the planets move the way they do? Well, it's because of gravity. So Kepler's laws explained how celestial bodies move. Gravity explained why they moved. So when two or more branches of science combine to create something new, this is a special kind of paradigm shift called a synthesis. And this particular synthesis is called classical physics. Now, I'm not going to go back and talk about how Newton investigated the comet and discovered gravity. We've already talked about that stuff. But what I will point out is that Newton, like everybody back then, was a very religious guy, a very superstitious guy. And but he believed in his science, and he tried to take these new laws of universal gravitation and apply it to explaining the universe as a whole, kind of like Ptolemy did 1,500 years before. Ptolemy tried to explain the entire universe as a coherent unit. So did Newton. It's been the dream of many a physicist and cosmologist ever since to be able to do this, to have a theory of everything. And so Newton attempted to apply this, but he was unable to do it. The problem is that every time he would try to calculate the movements of the planets, the system would be unstable. He would get a bunch of remainders in his math problems, a bunch of infinities. Like in the calculator, you get an E for error for an infinity. He would get these values, and he thought to himself, well, this suggests that the solar system should be unstable. The planets should be flying all different directions, and they should not be working together as a unit like they are. But clearly they are working together as a unit. Therefore, instead of interpreting that anomaly as a starting point for investigations, he put a God of the gaps argument there. And he said, well, it must be the hand of God keeping it all together. Now, it would take another 100 years before somebody would demonstrate that Newton had made a type 1 thinking error here. He had assumed that the hand of God was in play, and really it wasn't that. It was an even more interesting and amazing discovery, in fact, that would account for why the planets didn't seem to be behaving according to the laws. 1781, by accident, a man named William Herschel discovered a new planet. This was the first time that anybody had ever discovered a new planet. And at first he didn't think it was a planet. At first he thought it was a comet. And why would he think that? Well, because nobody had ever discovered a planet before. Anytime that somebody made a new discovery, it was a comet. So he looked at it through his telescope and observed it over a period of months and weeks. And he thought, as a matter of fact, he penned in his book, what a strange comet this is. It refuses to grow any fuzz, right? And over time, he began to realize that what he was looking at could not be a comet, and it must be a planet. So when he thought he saw a comet, that was a type 1 thinking error, right? It's a type 1 thinking error, by the way, if you remember, is a false positive. So you detect a pattern in the environment when there really isn't one. A type 2 thinking error is when you fail to detect a pattern when there is one. He made a type 1 thinking error thinking it was a comet. He was just wrong about it. But he eventually realized it was probably a planet. So he recognized this discovery as an opportunity to test Newton's laws of gravitation because, like any good scientist, he was totally aware of what Newton did. And Newton's laws were all the rage. They were as perfect as far as anybody could tell, but Newton did not apply them correctly. But all of a sudden, here's an answer to that mystery. Newton thought the hand of God was keeping it all together. Perhaps if I incorporate the gravity of that planet, it'll all work. It'll get rid of those remainders when you do the calculations. But it was a difficult task because he had to get enough observations of this new planet, enough observations of its orbit to make these calculations. And unfortunately for him, it would take 70 years to get those observations because the actual orbit of Uranus is 84 years. So they had to get at least 70 years of observations to make this work. And so it was his descendants that got it, right? But what they discovered when they got these data was that the observations still did not match what Newton's laws predicted. So they basically had to solve for X. They knew what all the other masses were for the other celestial objects because they had lots of observations of the orbits. They didn't know this other one over here, this new object. So it's like having an X in the equation. You have to solve for that. It took a lot of calculating. But what they were left with were some remainders. They were left with some infinities. So it still wasn't working. But they didn't throw the baby out with the bathwater like Newton did. They assumed there must be something else out there. So there was no God of the gaps from this point forward. It was only, let's try to explain this anomaly. And in 1846, after the orbit of Uranus had been determined, the data were not consistent with what was predicted by Newton's laws. So unlike Newton, his contemporaries did not make God of the gaps arguments to explain the anomaly, and instead they looked for alternative explanations. This is very important. One possibility is that there might be another source of gravity that was influencing the orbit of Uranus. This was a fascinating possibility, so they investigated it. And a man named Urbain Le Verrier, I think you say that, he used Newton's laws, much like William Herschel did, to try to calculate the possible orbital path that this mysterious unknown object might take. And after he did these calculations, he said, I've got some coordinates. I need you with the telescope to look at these coordinates and tell me what you see. And that's what they did. And what they discovered was a brand new planet, just as predicted. Now, sit back and think about that for a second. What a big deal that was. Not only a very short time earlier had somebody discovered a brand new planet, which had never happened before. Now, the laws of physics have predicted that something new would be discovered, and they followed those clues and they discovered it. This was the first time in history that something new about the universe had been discovered only by using the laws of physics. Everything else occurred because of an accidental observation. The laws of physics guided us to where to look, and we discovered something new. This is a big deal. It's an amazing feat, and it ushered in a new era of scientific discovery. So the discovery of Neptune proved the accuracy and the utility of Newton's laws, and they demonstrated the power of Newtonian physics as a natural science. Now, of course, everybody at this time is riding high on their horses. The scientists are like, we're about to discover the truth about everything. We're about to discover all of physics, and there will be nothing left to study. But there was one more anomaly in the solar system that needed to be explained. So they thought, we've discovered Neptune. We can explain this anomaly using the same technique. Or so they thought. So, many astronomers boasted at the time that they were on the verge of discovering everything there was to know. And at the time, there was one more anomaly known to astronomers that had yet to be explained. So they tried using this same approach that led to the discovery of Neptune to see if they could explain this anomalous orbit of Mercury. So it turns out that Mercury's orbit around the sun is strange. It behaves differently than any other planet out there. So basically what happens is that the orbit changes. And it changes at the point which it passes closest to the sun. So when the orbit changes, the scientists say it precesses. So when you see the word precesses, it means that the orbit's changing. And then it precesses at the perihelion, and the perihelion is the closest point to the sun. So here's what this looks like. So I'm going to play this video, and it's going to show the orbit of Mercury over the course of a period of time. And notice how the orbit changes. It changes ever so slightly. So it creates this three-dimensional pattern around the sun over the course of years. No other planet does this. And quite naturally, they thought, well, perhaps there's something tugging on Mercury. Just like something was tugging on all the other planets, like Uranus and Neptune. That's what was tugging on the inner planets, which is why Newton could not explain everything. Perhaps there's something unseen or undiscovered tugging on Mercury. So they suggested that it might be an asteroid belt. Well, they looked for it and could find no evidence of it. At one point, an astronomer looking through the telescope at the sun observed a new planet transiting the sun, meaning that you could see the shadow of it as it passes in front of the sun. And this new planet existed between the orbit of Mercury and the sun. So they thought, that's it. That must be it. And so they bought into the existence of this planet. They gave it a new name, and they called it Planet Vulcan, just like in Star Trek. Now, you've never heard of Planet Vulcan, I know, because it doesn't exist. But back then, they didn't have the internet. They didn't have instant communication. But it turns out that there was more than one scientist looking through a telescope at the moment that this new planet had been observed by this one scientist. And eventually those letters came back to the Academy of Sciences. And what they realized is only one person reported the existence of this and nobody else did. So what we're looking at here is an example of that error correction mechanism of science, where it requires multiple observation and replication for scientific observations to become fact. Because only one person observed it and nobody else did, they had to throw out the planet hypothesis. So what were they left with? Well, astronomers had to face the fact that Newton's laws failed to explain the movement of Mercury. And they just had to sit with the mystery, which, of course, was also something new because people didn't like to sit with mysteries historically. They liked to try to think up reasons. But in the absence of evidence, all they could say is that Newton's laws of motion just don't, and Newton's laws of gravitation don't explain this anomalous orbit. There must be something else going on. Let's wait until we get more information. And it would take until the 20th century before that would happen. Now, before we end tonight, there's one more anomaly I want you to know about. So there's the anomalous orbit of Mercury. But there's also some weird properties of light that could not be explained. Just one second. Hey, could y'all keep it down, please? All right. So light, it turns out, it's kind of weird. Newton did a lot of experiments with light. He invented new telescopes. He invented the reflecting telescope. And so he did a lot of experiments with lenses. Yeah, sorry. I was talking to my kids. So, Newton had imagined light. It could be a particle or it could be a wave. Right? So even that wave-particle duality existed back in Newton's time. But Newton did experiments that, to him, proved that it was definitely wave-like. And there were some anomalous properties of it, though. Now, to understand how they got to these conclusions, you have to kind of understand where they were coming from. Now, if light is a wave, then imagine what other waves are like in nature, because that's what they had to compare it to. And the only other waves that they knew about were sound waves. And of course, if you had like a calm pond, you could drop a rock in the pond and it would disturb the water and the waves would ripple outwards, right? So in both of those instances, in terms of sound waves and in terms of waves on the water, the wave had to propagate through something. It had to travel through a medium of some kind. In the case of sound, it's the air. In the case of the water ripples, it's the water. So the thought was this: if light is a wave, then it must travel through something. But it was a puzzle because they were trying to figure out what this stuff was. So they got big vacuum tubes, big, glass tubes that were transparent, sucked all the air out of them, made as perfect of a vacuum as they could make it. And then yet light could still travel through them. So they were puzzled. They were like, well, it must be there. This medium must be present. So how can we create an experiment to try to discover this? And so the discovery of this medium, something they called the ether, was what consumed astronomy and physics during the 19th century. Okay? So they were attempting to try to discover this stuff. So let me, the first opportunity that they had to try to test for this ether was in the mid to late 1800s, when they invented, these guys, Michelson and Morley, invented a very ingenious device called an interferometer. Now, at the time, this device was the most expensive scientific instrument ever invented. It cost, in today's dollars, the equivalent of $750,000. Now, that doesn't seem like a lot, but back then, that was a lot. Nobody spent that much money on a scientific instrument, but these guys did. And basically what it consisted of was, you could see it on the bottom here. There's a huge concrete slab. And you can see this round device down here. That is a pool of mercury. And they suspended this concrete slab on the top of this pool of mercury so they could rotate it back and forth. They needed it to be heavy and solid so they could protect it from vibrations. And they had it deep in a basement in the University of Ohio, in fact. It was deep in the basement of a building to shield it from the vibrations of the horse and carriages that were in the streets above. What you're looking at here are, in this apparatus, it's basically designed to take a single beam of light and split it and lengthen it into two different beams, and then recombine those two beams back at a common source. And I'll have a model I'll show you. It'll make a lot more sense. But basically, you have a source of light, which was a candle, and you have these series of mirrors here. The ones in the middle are half mirrors, meaning kind of like sunglasses. They let half the light through and they reflect the other half. And then the mirrors on the edge here are full mirrors, right? So they reflect all the light that hits them. And so the idea was this: there's a constant blowing. Sort of confused because these chapters have been describing that all this mysterious stuff in history was in fact actually perfectly scientific, and just the ignorance of the man that made it seem supernatural, right? Then is that the point of the class? That even strange supernatural things are explainable by science. So, okay. The use of the supernatural there is a misnomer. The scientist isn't going to say it's supernatural. Okay? That's what they've learned through this process. So the supernatural, if you have that as an explanation, it's not an explanation. So if some event happens that you can't explain, and you say, well, it must be it must be something supernatural. That is a stopping point, right? And the proof of that is in the fact that no scientific discovery had been made about comets for over 1,500 years, when everybody was just assuming they were messengers of the gods, right? And then Isaac Newton came along and assumed it was a natural thing and attempted to explain it. And that was the moment that physics was created. So yes, anything that is unexplainable does not mean it's supernatural. And to say it was their ignorance, yeah, it was ignorance. But when you discover an anomaly, so we're talking about the supernatural things, those are anomalies in science, then that is your opportunity to try to explain it. But bear in mind, they did not have these explanations then. Okay, because we've got our own modern anomalies. I'm talking about the history of them here. So, yeah, so that even strange supernatural things are explainable by science. I will say this: if any event can happen in the natural world, it is explainable. It may not ever be explained, but it is possible to explain it because it has natural causes. So, it doesn't mean it will ever be explained, but it would be possible to do so. Because if it can happen, then there are causes, and those causes could be discovered, given the right circumstances. So yeah, I guess the lesson to be learned here is that be careful in attributing things to the supernatural. Be very careful. Because time and time again, where people have put God of the gaps, there's not been a single instance in all of human history where they've been right about it. And it's just a matter of time before science comes along and explains it. And then you have to move your God of the gaps to something else. Yeah, that was a really good question, actually. Okay, so let me just kind of show you how this works. It'll a picture's worth 1,000 words. So let me unshare the screen here, and I'm going to share a different screen. It's really an amazing experiment. That's why I get so excited about talking about it. Because this interferometer is a very sensitive instrument. Now, what you're looking at here is that device. But it's like you're attached to the ceiling and looking down on the top of it. Okay? So these arrows that are moving, let me make sure I've shared with the right. Let me make sure I share it with, optimize the video. There we go. Okay, these arrows that are moving, that represents the ether, right? And the assumption was that this ether is everywhere. This is the medium through which light propagates. That was the belief. And it's everywhere. And so the Earth is in orbit around the sun, right? And this ether is out there. And sometimes the Earth is moving against it. Sometimes it's moving with it. So the ether wind, the ethereal wind, is blowing in a particular direction. And as the Earth travels around the sun, sometimes we're going against the wind. And other times we're going with it. And the thought was this. What this device does, let me just turn it. This arrow right here, this yellow arrow, represents the candle. That's the light source. And what it'll do is the light source will be directed towards this half mirror. 50% of the light will be reflected off of it to this mirror, and then it will be reflected back to the observer. This is the eyepiece that they looked through. The other half of the light will pass through this mirror, be reflected off the full mirror and back again, and then back down at the observer. So what you're looking at here is like they're drawing like a light sail, right? You have a beam of light going this direction, and you have a beam of light going this direction. And if you turn it like a sailboat, like a sail in a sailboat, if you turn it against the wind in particular ways, it's going to blow one beam in a particular direction and the other beam in another. It's going to slow down the progression of light from one direction versus another. And what that would do is it would produce a distorted effect in the where did I put that? Hold on a minute. There it is. It'll produce a distorted effect in the lens that they looked through. So this right here I don't know if you can see that screen. I think you should be able to. Is an example of this distorted effect. It kind of bends the light in a particular direction if the ether's there. So let me show you what that does. So let's turn it. Let's just leave it where it is right here. And I'm going to hit play. There's the light beam. Half of it is reflected one direction, the other half the other. Notice that this beam has to travel against the ether, so it slows it down. And when those light beams recombine, it creates a distorted image. And so by turning the device in particular directions, you can, based upon how the light gets distorted, you can derive properties of the ether. You can begin to study its properties. So, come on now. Oh, I have to restart it. Oh, come on. There we go. It's okay. It froze on me. Hopefully, okay, so wait. So what exactly is the ether? Okay. The ether is like the water. When you drop the pebble in the water, that causes the water to ripple, and that creates a wave, right? And that wave travels through the water. Light was understood to be a wave, right? And the reason they thought that is because you have these lenses, and you have prisms. You could split apart the light into different colors. So the different colors must mean that there's different sizes of waves, right? Some of the waves are longer, some of the waves are shorter. And so that's why when they go through the prism, the ones that are traveling faster get deflected at a different angle than the ones that are traveling slower. And that's why you get this rainbow pattern. So that's where the idea that light was a wave came from. Now, when they were trying to study this as a wave, as light as a wave, they thought, well, all waves that we know about in nature must travel through something. Kind of like the waves in the water have to have water to travel through. And sound waves have to have air to travel through. The thought was this: there must be something out there that light must travel through in order for that wave to exist. And so this was designed to try to discover that stuff. And they referred to it as the ether. Now, you may be confused because you've never heard of ether before. But that's because the ether was a type 1 thinking error. It doesn't exist. And this experiment proved that. So let me go back real quick. I know I told you to make your brain hurt, but I'm glad you're asking these questions because these are important events. So remember, these guys spent a ton of money on this experiment, and their job was to try to discover the ether. All right? And they had to go back and tell their investors. Well, they said, well, what did you discover about the ether, Mr. Michelson and Morley? I said, well, the ether doesn't exist. And they're like, what? And think about that. They were wondering how the hell a wave could exist and propagate through a vacuum. If there's nothing in the vacuum, if a vacuum is nothing, how could light travel through a vacuum without something to travel through? It completely blew their minds. It was an anomaly that they could not explain. In addition to that, there's something else about light that's very strange. They were able to get a very precise measure of the speed of light. And they measured it at 300,000 kilometers a second. But the interesting thing about that is that they got that measure no matter which direction they looked. So that means even if you're traveling towards the light source or away from the light source, no matter which way you look, light was going the same speed. To imagine what that means in real life terms, because no other phenomenon behaves this way. Imagine that you're standing on top of a train, a locomotive, and you've got a baseball in your hand, and the train is going 30 miles an hour in a particular direction. You're at the front of the train, you take your ball and you throw it off the front of the train, And let's just say that that ball is going at 10 miles per hour. The train is going at 30 miles an hour. You throw the ball off the front of the train at 10 miles an hour. How fast would the ball appear to be going to somebody on the ground if the train's going 30 and the ball's thrown at 10? 40, exactly. You just add the speed to it, right? You throw it off the front of the train. It adds its own speed to the total amount of speed that, if you're going 30 miles an hour, you throw it at 10, it's going to be 40 miles an hour. That's not what light does. If you're at the front of a train and you have a laser pointer and you shine that laser pointer off the front of the train and that train's going 30 miles an hour, no matter what, the light that's measured on the ground is going the same speed. If you shine that light behind you as the train's going a particular direction, it's going the same speed. It doesn't matter what you do to the light. The light goes the same speed. So how did they measure the speed of light? They measured it with that device, the interferometer. Here, I'm going to put the link to that device here so you can learn more about it. Just a second. Let me, because it's worth it to, if this is interesting to you, you should look into it, because it is an absolutely fascinating outcome. That light does not behave like anything else. Its speed is constant, no matter if it's coming at you or going away from you. It is a deep, dark mystery for that time, and so was the fact that light could travel independently through a vacuum without anything to travel through. They could not explain this. They could not explain why light did what it did. They could not explain why mercury did what it did. So they had to sit with this mystery until the 20th century. So that's it. Last question. What two anomalies could not be explained by classical physics? You're going to pick two answers. Is it the perihelion precession of Mercury, meaning that Mercury's orbit changes? Is it the origin of sunspots? Is it the origin of lightning? Or is it why light doesn't need a medium to propagate and why its speed is constant in a vacuum? We're going to get done a little early tonight. So just got 10 more seconds here. Okay, let's see what you put. Good. The correct answers are A and D. Now, it took until the 20th century before this mystery was solved, and it took a very, very smart guy to do that. Does anybody know who that was? That explained it. What his name was? Einstein, yes. Einstein. Now, it took a great leap of imaginary thinking, because what died in classical physics, whenever these anomalies could not be explained, they knew that Newtonian physics was not totally correct. It was very precise, but it wasn't the whole picture. And the reason they were looking for this ether and everything like that was because they were looking for analogs in the environment to explain these phenomena. Analogs of the rock falling into the pond, or sound traveling through the air. And the reality was that it was at this point that science left the common sense. And what's required in modern physics is to separate yourself from how the everyday world works, because that is not sufficient to explain the way the universe actually is. And the way that it actually is is going to blow your mind if you don't know about it. I know some of you probably do know about it, but I guarantee you that most of you, your concept of gravity and what it is as a force between two objects, that's Newtonian in interpretation. In order to explain these anomalies, Einstein had to completely reconceptualize gravity and what it was. We still have gravity, but our understanding about what it is far different than what you probably think it is. And it's going to blow your mind when you find out what it actually is. So anyway, that's okay. Just shoot me an email, and I can hook you up with those points. But do remember the correct answers, because these kinds of questions are what appear on the quiz, if you know what I'm saying. All right. Any questions? Go ahead and ask them. You can hit the space bar and speak, or you can put them in the chat.
I had a question.
Sure.
So the question's more about, sorry, I'm seeing somebody else's face. It's making me hard to think. So my question's more about the slides.
Sure.
So for most classes, I watch you presenting live, and then later I download the slides and write notes on them, but
right.
I can't download your slides.
Yeah, this time, because I didn't finish the entire set. I had to split it across 2 class periods, but I'm going to go ahead and make it available to you right now.
For the previous lectures?
So there you go.
Will that be in Canvas, or will that be on Top Hat?
They're on Top Hat. So you should be able to download it now out of Top Hat. Now, what I should have done was go ahead and make the slides that we had covered available to you, which I can do. I just forgot to do that.
Okay.
So I'll do that. Okay?
Thank you.
No problem.
I also had a really stupid question.
Oh, go for it.
So talking about gravity, do we have 2 different types of gravity? Like, does Earth have a gravity that keeps us standing, and then Sun has a gravity that helps the planets rotate?
Yeah, so any object with mass has gravity. So, the Earth has mass, so it has gravity. And actually, we're going to explain all of that in the next class. I don't want to get too far ahead, because I want to surprise you. Yes, you do have gravity. Yes, you do. And when you find out what gravity actually is, it's really going to make you think. Because we think of gravity as this attractive force, but that's not what it is, actually. So any object that has mass has gravity. And gravity, it turns out, is an emergent property of something far deeper. And I just can't wait to tell you what it is. I'm not going to tell you tonight, though, because I don't want to ruin the surprise. But yes, so the sun is the dominant force of gravity in the solar system. But you know what else has gravity? Is our own galaxy. And our own galaxy is what keeps us where we are in the galaxy, and we travel around it. And the central black hole, the supermassive black hole at the center of our galaxy, is what kind of is the linchpin that's holding it all together. But in addition to that, you have this stuff called dark matter that is far more numerous. I mean, it accounts for 95% of the gravity that's in our universe, and it's made of stuff we can't detect except for the gravity that it exerts. And we live in a halo of this stuff. It surrounds our galaxy, and we know it's there because the way the stars in our galaxy move give it away. And for example, if our solar system, the objects that are closer to the sun revolve more quickly around the sun than do the objects further away. So, Mercury is traveling around the sun at a higher rate than Earth is, and at a higher rate than Mars, and so forth. So, Mars is going slower, and the further out you go, the slower you go. You would think that would be the way that the stars in our galaxy work. So the ones going around the center of the Milky Way's black hole should be going around much faster than the ones out on the edge, right? They should be going faster, and then as they go out to the edge, they go slower. That's not what they do. the stars in our galaxy are more or less moving in a uniform fashion. They're moving together. And the only way to explain that is that there must be something else that's supermassive that the galaxy is embedded in that is influencing it. So, what do you think? We're going to talk about the many worlds interpretation. I don't want to get too far into it. We're about to get into that stuff. Yeah. Well, no, you're not screwed because the attendance is extra credit. The attendance point. However, if you were in class and you answered a question and I have some proof that you were in class, just shoot me an email. I'll give you the attendance point. Yeah. Well, the universe expanding into itself. We're actually going to talk about cosmic expansion. So this is all stuff that we're going to get into with modern physics. And I will show you direct evidence, direct proof that there was a Big Bang. I'll show you all of that stuff. And then we'll talk about what it means. And we'll talk about cosmic expansion and all of this stuff that you're asking about. And we'll talk about the many worlds hypothesis. We're going straight there. Yeah, the CMB, the cosmic microwave background. I'll show you pictures of it. It's going to be a lot of fun, I think. To me, that's where all of the really interesting stuff is. We had to get through this arduous kind of... It's still interesting to me, but dry to a lot of people. But most people are going to find modern physics to be fascinating because it is completely beyond imagination. And not only is it just beyond imagination, a lot of it's turned out to be true. So there's a lot of stuff that's been proven. Okay, any questions before we go? All right, nothing heard. Thank you all for coming, and thank you for sticking around in the class, okay? I really do appreciate it, and I appreciate the questions. Yeah, you guys have a good weekend. It is Thursday. Yes, I will see you on Tuesday, okay? And then, by the way, Tuesday we'll cover modern physics. We'll finish that on Tuesday. That means next Thursday, we're going to have the quiz review. So make sure you're here for that. All right. Guys, have a good night.